here we are. Oops, sorry, I didn't scare you. Here we are with the third lecture of the material in Chapter 6. And again, we are looking at a new type of equilibrium relationship. We've done gas liquid or vapor liquid, and then we did solid liquid, and now we're doing liquid liquid. And next semester in thermodynamics, you will learn the principles of these equilibriums. But for now, we're just looking at carrying out the mass balances using the information from the equilibrium. So we're going to learn two things today. We're going to learn this distribution coefficient, and we are also going to learn how to use diagrams. Okay, and in this case, it's going to be liquid-liquid equilibrium. So when we have a liquid-liquid system, what happens is that it's more thermodynamically favorable when you mix compounds that you form two separate liquid phases. One single phase would not be stable thermodynamically. So this is, you've done this in your class. You've done, if you had an organic lab, you must have done an extraction. You're trying to get species B out of the C phase, so you add in A. And A then can pull out B from the C phase, and then you are able to dry it or some other way of getting the B purified, which you otherwise were not able to do in the C phase. So this is called liquid-liquid extraction. And when you have a third component that partitions between the phases, such as B here in this diagram that we have, okay, we have two liquids. A and C are essentially immiscible, okay, and B partitions between them. So the distribution coefficient or partition coefficient is usually written as K, and you define it. I mean, you can define it however you want, but in this case, it's defined as the mass fraction of B in the A phase divided by the mass fraction of B in the C phase. So that's, if you have that information and it's empirical, okay, you would be able to you have to measure that. Then once you have that information, you can use that to complete your material balance. And we'll see how we do that shortly. Okay, so here's a case. We are given the distribution coefficient, K, of styrene distributed between the ethylbenzene and ethylene glycol at 25 degrees C. So B is the styrene, and A is ethylene glycol, and C is ethylbenzene. Okay, so now you're given this value 0.19. Mass fraction, it's defined here, mass fraction of the ethylene glycol phase per mass fraction of styrene in the ethylbenzene phase. Okay, so now we have 100 grams, so we're given some material balance information. 100 grams of pure ethylene glycol is added to 120 grams of a mixture containing 75 weight percent ethylbenzene and 25% styrene, and the resulting blend is allowed to equilibrate. How much styrene transfers to the ethylene glycol phase, assuming that ethylene glycol and ethylbenzene are immiscible? So now we have to carry out our mass balance. I'm doing this. I would, if I were giving the lecture in the class, you could solve it and we would do a poll everywhere. But so let's go ahead and do the calculation. So this is our mass fraction. The mass fraction of B in the A phase divided by the mass fraction of B in the C phase is equal to 0.19. Okay, so now we're going to just write all that out here. So what I have done is I have selected M of B. So we know what we have going in. Okay, we had 120 grams of ethylene glycol and we have a mixture, we have 120 grams of the mixture. We have 100 grams of ethylene glycol. So of this 120 grams, 25% is styrene and 75% is ethyl benzene. So we can figure out exactly what we have going in. So what we don't know here is I'm defining one variable here. We're going to have one equation and one unknown. And our one unknown is how much of the B is, what is the mass of B in the A phase? Okay, so we can use that one term, excuse me, and write out an equation that we will solve. Okay, so this is the mass fraction of B in the A phase. Okay, so this is the mass of B in the A phase divided by the total mass of the phase. So we know that we had 100 grams of the ethylene glycol going in. So the total amount in this phase is going to be 100 grams of ethylene glycol plus whatever B goes into that phase. So this is now, the upper part of this equation is now the mass fraction of B in the A phase. And now what we're going to do is we're going to divide it by the mass fraction of B in the C phase. Okay, so this here is the mass of B in the C phase. It's what we started with. Okay, 25% of the 120 grams is styrene. And we're going to subtract the amount that is in the A phase, and that's what's in the B phase. Okay, divided by the total mass of the C phase. Okay, which is going to be 120 times the 75%, that is ethyl benzene, plus the amount of B in that phase. Okay, so now we have a nice clean equation. I'll clean it up for you. There we go. There it is. Beautiful. And now you have to solve the equation. Okay, you can do this. Since we have tools, I guess I would solve it using Excel. But here's the solution. Okay, is 4.39 grams is M of B. Okay, so now we're going to look at 3 liquid phase equilibrium. And this is usually represented by a phase diagram, which again, I point out phase diagrams are this is a thermodynamic concept. Okay. But what we're going to do now is we're going to study this phase diagram, and I'm going to show you how to use it. So this diagram has acetone, water, and methyl isobutyl ketone. Okay, MIBK. And on this diagram, you see there is a phase envelope. And this is the phase envelope, okay? And so everything below the phase envelope is 2 liquid phases. And everything above the liquid phase, above the phase envelope, is 1 liquid phase. We've got 1 phase here and 2 phases here inside. Okay. Now, these points, the axes, are 100% of whatever the compound is. So this point here is 100% MIBK. This point here is 100% acetone, and this point here is 100% water. All right, so we are going to learn how to read this diagram. Okay, so here we go. We'll look at it as a calculation problem. We have 5 kilograms of 30 weight percent acetone and 70% water. Okay, you can figure out what you have. There's a total of 5, and 30% is acetone, 70% is water. Okay, so you can figure out what those amounts are. Is added to 3.5 kilograms of a 20 weight percent acetone, 80% MIBK mixture. Okay, So this is solution 2. It's got 0.7 kilograms of acetone plus 28 kilograms of MIBK. So what we're going to do with those is we are going to combine them. Okay, so we have a total of 2.2 kilograms of acetone, 3.5 kilograms of water, and 2.8 kilograms of MIBK. That's the total amount. So now what we need to do is plot that on this diagram. So let me show you how to plot that. Okay, so we've got, first we need to turn those into mass fractions. Okay, so this, on a mass basis, the overall composition is 25.9% acetone, 41.2% water, and 32.9% MIBK. So let's look at how we do this. I'll start with, I'm going to show you on the previous slide, we're going to find the point of 25.9% acetone and 41.2% water. Okay, 29.5% acetone. We're going to go down the acetone until we come to 29.5, which is going to be right about there. Okay, and then we had, I forgot already, 41.2% water. Okay, so here's water. We're going to ride the water line down to 41.2. Okay, so here's about 41.2, somewhere around there. Okay, and so what we're going to do is we're going to find where these two intersect, and it's going to be right about there. Okay, and the third one, it necessarily has to be. So we can, let's look at this and figure out what the MIBK is. Okay, here's the MIBK. We're going to go down, and this point is around 29% or 30%? 32.9. Okay. All right, so you just kind of do the best you can, find the spot. And now I've plotted it here more exactly. But the key here is that this is the overall mixture, but we have two liquids. And on the phase diagram is going to tell us the composition of those two liquids. Okay, we're going to go to this. We'll use a tie line here. This will be the composition, and this is going to be the MIBK rich phase. And this one here is going to be the water rich phase. So now we have to go again and read those numbers. All right. So here we have, this is the water. Okay. So it's like 6% water. Okay, I've got it here. 6.5% water. And the MIBK is going to be, we're going to come down here. This is it here. Okay, so we're going to have like 62% MIBK, and the rest is acetone. And we do the same thing on the other side. On the other side, we have this point here. Okay, so it's like 4% MIBK. All right. And the water is about exactly 75%. Okay. And then the rest is acetone. Okay, so hopefully you understand how to read the diagram. So now once we have the diagram, we know what we've just gotten is the composition of the two phases leaving the extractor. Okay, with that information, we have two unknowns here, 1 and 2, and we can solve for the unknowns. Okay, so there are 3 possible balances. Okay, but we only need to choose 2 of them to get M1 and M2. So let's see. If we write those out, okay, we do an overall balance. M1 plus M2 is equal to 8.5. So what goes in is going to come out. And then we're going to do a water balance. Okay, so we have 3.5 kilograms of water going in, and we use the mass fractions times the M1 and M2 coming out. And we can now solve and get that M1 is 4.2 kilograms and M2 is 4.3 kilograms. Okay, so now this next one is almost identical, okay, but I've changed the amount of water. So now you can do this problem for the video quiz.